In the last video, I talked about what it means for a computer to be Turing complete and why we need to build a conditional jump instruction in order to make this computer Turing complete. In this video, I'm going to actually build the hardware for conditional jump. Now, in that last video, I asked you what condition might make sense to use for the conditional jump, and the two most common things y'all mentioned were to jump if the carry bit is set after an addition or subtraction operation, and jump if 0. And since a number of people suggested both of those, I figured I'd implement both of them. So jump on 0 is straightforward enough. It just means that if the result of a computation is 0, like it is here, then jump to a particular address. Otherwise, just keep executing the program. So if the result of this addition here works out to be 0, then jump to address 9 and do something down here. Otherwise, just continue to address 7 and do something else. And then we may end up skipping address 9 with the jump instruction later on. Jump on carry means that the result of a computation, for example, adding two numbers, if that result can't be represented with just 8 bits, then jump to a particular address. Otherwise, continue executing the program. So if the answer to this addition works out to be more than 255, like in this case here, we've got, I think this is 200 plus 100. If the result, 300, can't be represented with just 8 bits, then jump to address 9 and do something down here. Otherwise, continue to address 7 and do something else, and then skip address 9. So I'm actually going to build both of these, the jump carry and the jump 0 instructions. Even though technically to be Turing complete, we really only need a single conditional jump instruction of some kind. So either the jump 0 or the jump carry would be enough. But having more variety of instructions like this available just means that we can often find more efficient ways of writing particular programs. So it's nice to have a variety of different instructions. Now I'll start with the jump on carry instruction. Now it might seem like kind of a weird thing to have an instruction that says jump if the result of an operation, like addition, doesn't fit in 8 bits. But it turns out it can be useful, though I think the biggest reason to add that instruction is because it's relatively easy to do. Remember, we're using two of these 74LS283s in our adder, and the 74LS283 is a 4-bit adder. And remember, the way we're able to chain two of them together to get an 8-bit adder is by connecting the carry out of one over to the carry in of the next one. And that's this connection right here. The carry out of this chip is going to the carry in of this chip here. So if the result of adding the first 4 bits doesn't fit in 4 bits, then we can kind of carry the 1 into this 5th bit. Well, if the result of adding all 8 bits doesn't fit into 8 bits, there's another carry signal coming out of this second chip right here that we're not doing anything with yet. And just to see what that looks like, we can hook an LED up to it. So here we go. It's currently not set, which makes sense because we're adding 0 plus 0, and the answer is 0. And of course, 0 fits within 8 bits, so the carry bit's not set. So now let's load a value into the A register. So this is 200 in binary, and so we've got 200 plus 0. The sum is 200, as you'd expect, and 200 also fits within 8 bits, so no problem there. Carry bit's still not set. But now let me put something into the B register. Okay, so this is 100 in binary, and so now we've got 200 plus 100. Well, the result should be 300, but 300 doesn't fit in 8 bits because with 8 bits, we can only go up to 255. So instead, what we have here is 44, which is the remainder we're left with since we don't have a 256's place. But instead, the carry bit is set. And so this tells us that the answer in the sum register isn't really the sum of 200 plus 100, which might be a good thing to know. But it also means we know that we have the raw information that we need in order for our jump carry instruction, which is very convenient. And the other instruction that a number of you suggested building was a jump on 0. And that just means that if the result of a computation is 0, then jump to a particular address. Otherwise, keep executing the program. So how can we tell if the result is 0? Well, unfortunately, we don't have a single bit sitting around that just tells us whether the result is 0, like we did with the carry bit. So we need to build some logic. So how do we know if a number is equal to 0? Well, it's going to be equal to 0 if each of the bits is a 0. And so how can we tell if all 8 bits are 0? Well, we could use a NOR gate. So if you look at the truth table for a NOR gate, you can see that the output goes low anytime any of the inputs are high. Or in other words, the only time that the output is high is if all of the inputs are low. So if we had, let's say, an 8-input NOR gate, we could just hook all 8 bits of our number up to the 8 inputs of the NOR gate, and the output would only go high if all 8 inputs were low. In other words, it would tell us if our 8-bit number was 0. Now you can get 8 input NOR gates, and if you've got one, you can definitely use it, but I don't happen to have any, but that's okay. We can actually build it with this one. And this gives us 4 NOR gates, and so what we could do is hook 2 bits up to each, and then that will tell us if each pair of bits is 0, and then as long as all of the pairs of bits are 0, then we'll know that the whole number is 0. So we need to take the outputs of these 4 NOR gates and AND them together. And so to do that, we can use some AND gates. And again, it'd be nice to have a 4-input AND gate, but if all we have is 2-input AND gates, we can work with that. So what I'm imagining is we'll build something like this. So if both inputs are 0, this is a 1. If both inputs are 0 here, this is a 1. If both of these are 1s, then this is a 1. And then the same thing down here, and if both of these are 1, then this is a 1. So the output will be a 1 if all of the inputs are 0. Otherwise, the output will be a 0. So this circuit here will let us determine whether our 8 bits input are all zeros. And then we can use that to control our conditional jump. So I'll build up that 0 evaluating circuit over here in some space that's free near the ALU. So this is the 74LS02 with the 4 NOR gates that we'll use to NOR each pair of bits. And this is the 74LS08 with the 4 AND gates that we'll use to combine those. And of course, we'll just use 3 of those AND gates. Like any of these other chips, I'll hook up power and ground to each of them. So I'll start by connecting the logic between the gates before I worry about hooking up the 8 inputs. So the outputs of the 4 NOR gates are going to go to the inputs of 2 of the AND gates. So I'll hook the outputs of the 2 NOR gates on the bottom to the 2 inputs of one of the AND gates on the bottom. And I'll hook the outputs of the 2 NOR gates on the top to the 2 inputs of one of the AND gates on the top. So that's these 4 connections. And so next I'll connect the outputs of those 2 AND gates to the inputs of a 3rd AND gate. So the output of that top AND gate is right here, and we'll just connect that right over to the input of the AND gate next to it. And the other input comes from the output of that bottom AND gate going into the 2nd input on the top. And the output of that 3rd AND gate is going to tell us whether we've got a 0 or not. So for now, I'll just hook that up to an LED so we can see whether we've got a 0. Next, we need to hook up the inputs, the 8 inputs here, which is going to be the 8-bit register that we want to check if it's 0 or not. Now, I could hook this up to the 8 bits of the A register, and that would tell us if the A register is 0, which would let us build a jump if A is 0 instruction. But I'm actually not going to do that. Instead, I'm going to hook this up to the sum register because that gives us some more flexibility. Now, why is that? So first, if we load a 0 in the B register, then the sum register will be the same as the A register. Since it's A plus 0, it's going to be the same. So we haven't lost anything by looking at the sum register rather than the A register. We can still use this to build a jump if A is 0 instruction, even though we aren't looking directly at whether A is 0. But it also means if we wanted to, we could write microcode for even more conditional jump instructions, like jump if A equals a particular value. So for example, if we wanted to jump if A equals 5, like it does here, then we could put a 5 in the B register, turn on the subtract bit, so we're subtracting B from A, and since A equals B, when we subtract, we get a 0, and so we could jump if A equals 5. So hooking our new 0 detecting circuit up to the sum register is definitely the way to go, since I think it'll give us a lot more options. So I'll hook each of the 8 bits of the sum register up to the inputs of our 4 NOR gates. And it doesn't really matter which bit goes to which input or which gate, since we're really just trying to tell if they're all 0, so it doesn't matter what order they're in. Okay, well now that's all hooked up, so if we hook up power here, we can see that the output is on. So the 0 is on, which is good because we've got a 0 here in the sum register. So let me put something else in the sum register, and we see our 0 signal turn off, which is good. So it seems like it's, at least initially, it seems like it's working. Okay, so now we've got our carry bit and our 0 bit. So how are we going to go about using these to build conditional jump instructions? Well, it turns out that there's a problem with the way that these are set up right now. And to see what that problem is, let's take this snippet here from a potential program where we're trying to do a jump if carry instruction. And so what we're trying to do here is we're trying to add some value that's in memory address 15 to the A register. And then if the result of that addition is greater than 255, in other words, it sets the carry bit, then we want to jump to address 5. Otherwise, we'll just want to continue executing the program. Now, in order to see what the problem is here, I've written out the micro instructions for the add command. And remember that all of our instructions are made up of micro instructions. So the add command, you've got the 2 fetch instructions, which are common for all of the instructions, and then the 3 additional micro instructions that the add command has. And so I've just written out the control word bits that are set for each of the 5 steps of the add instruction. And so we can go step by step and see what the problem is that I'm talking about. And so let's say we're running a program and we've got a value of 254 here in the A register like we've got, and we come across these instructions. So let's step through that. So the first 2 micro instructions here for any instruction are fetching the instruction from memory. So I'll just step through both of those. And once I've stepped through both of those, we've got the add instruction here in the instruction register. So the opcode for add is 0010, so we've got that. And then the 15 here is the 1111. So the next micro instruction in our add instruction is saying instruction register out, memory address register in. So we're going to move this 15 to the memory address register, and there it is. And that lets us get at the value that's stored in memory at address 15. So then the next micro instruction is going to take that value from memory and put it in the B register, right? So that's RAM out, B in. So it's going to take this value, put it in the B register. And now that we've done that, you can see we've got 254 plus 3 equals 1. Well, of course, 254 plus 3 doesn't actually equal 1. It equals 257. But since 257 doesn't fit in 8 bits, it wrapped around and our carry bit is set, as you can see here. Which is great. You know, the next instruction is a jump if carry, so that means we'll want to actually do the jump. But we're getting a bit ahead of ourselves because there's still one more micro instruction here before we're done with our addition. And this last micro instruction takes the result of the addition and puts it in the A register, right? So sum out A in, because when we say add 15, you know, what that means is add the contents of memory address 15 to the contents of the A register and then put the result back in the A register. So let's do that. Okay, so now our 1 has moved into the A register here, and we're done with the add instruction. But we've got a problem. What happened to the carry bit? Yeah, the add instruction we did resulted in a carry, right? We did 254 plus 3. We got 1, except there should be a carry. And the next instruction is a jump if carry, so it needs to know about that. But we've lost that information. So what do we do about that? You know, how do we keep track of whether this add or subtract instruction that we're doing here resulted in a carry or not if at the end of the instruction the carry bit isn't set anymore? Well, what we've got to do is that on the last micro instruction here, where we take the result and put it into the A register, we've also got to take the result of the carry bit and the 0 bit for that matter and put them somewhere. So how can we store these 2 bits somewhere where we know they won't change unless we explicitly update them at a particular time during the execution? Well, what we need is basically another register. You know, just like we're taking the result of this addition from the sum register and putting that into the A register, what we want to do is take the result of the carry bit and the 0 bit and put them into their own special register, which in our case, what we'll do is we'll create another register and we'll call that the flags register to keep track of the carry flag and the 0 flag. And having a flags register to track things like this is actually pretty common. So for example, this is what the flags register for the Intel x86 processors looks like. You can see it's a 32-bit register with a number of the bits used for different things. But even a popular modern processor like this has a carry flag, just like what we're building, and a 0 flag, just like what we're building. And you can see down here it talks about the carry flag. It says it's set if an arithmetic operation generates a carry or borrow out of the most significant bit of the result, cleared otherwise. And that's exactly what our carry bit does. It indicates an overflow condition. And the 0 flag, set if the result is 0, cleared otherwise. So this is exactly what we're building. And if you're interested in some of the rest of this stuff, you can check out the whole Intel Developers Manual, which I'll put a link to below. But you can see, even a modern processor might have over a dozen or so flags with, in some cases up to 64 bits reserved for the flags register. But our flags register only needs to hold 2 bits, for the 0 and the carry. So we can use one of these same register chips that we use for most of our other registers. One of these 74LS173s, will hold 4 bits. So that's more than enough for our 2-bit register. So basically, the plan will be to take these 2 status bits, the carry bit and the 0 bit, and feed them into 2 inputs of the flags register here. So these are the inputs along here. And then we'll be able to control when they're read in using the data enable signal and the clock line. And once it's latched those values in, then they'll show up here on the outputs. And so it's the outputs here that will reflect the current value of the flags register. So let's hook this up. I'll start by disconnecting power from the computer, and I'll connect the power and ground pins of our register chip. Okay, so now we've got 5 volts hooked up to VCC here. We've got ground hooked up to ground. And so now we're just going to go, pin by pin and figure out where we want each one hooked up. So pins 1 and 2 are M and N, and those are the output control. And in our case, we want the output to always be enabled. These are just ANDed together and they're active low. You can see little inverter things there. So we want to tie both of them low in order to have the output enabled. And since we always want the output enabled, I'll just tie both pins 1 and 2 to ground. So here's pin 1 to ground and pin 2 to ground. Next, if we look, we've got our 4 outputs, 1Q, 2Q, 3Q, 4Q. Those are just the outputs. And so that'll actually tell us the value that's in the flags register. So for now, I'll just hook those up to LEDs just so we can see what's in the flags register. And since we're only using 2 bits from this 4-bit register, I'll just hook up 2 of the LEDs. Next is the clock input. And remember that a register is made up of flip-flops, which store the input value at a particular momentary point in time, which is determined by the rising edge of this clock. And so we want this register to be synchronized with all the other registers so that when we're capturing the result from the sum register, we're also capturing the flags at the exact same moment. And so I'll hook the clock input for this register to the same master clock that's synchronizing the rest of the registers. Next are these G1 and G2 signals. And these are data enable signals that control whether the register is reading its input and updating its output on this clock pulse, or whether it's not updating and just holding on to whatever value is already stored in the register. And we definitely want to have control over the timing of when this register gets updated. So this data enable will need to be controlled by the control logic. So we can have an explicit microcode instructions telling it when to update. So for example, in our add instruction here, we'll want to update the flags register at the same time, as part of this same micro instruction where we capture the result of the A register from the sum register. And like the output control, there's 2 of them, but they're just ANDed together. So I'll just connect both inputs together so they're always just the same. And for now, I'll just set this high, which is inactive since it's an active low input. And that way we can manually set it to test it out before we hook it into our control logic. And next we get to the inputs for our register, and these are pretty straightforward. We're just using 2 of them. One is going to come from the carry bit here. And the other is going to come from the 0 bit down here. So we've got our carry bit and our 0 bit going into the register here. And then when the register is enabled to latch in its input, it'll latch that in and store it here on the output of the register. And finally, there's this clear pin, and this just overrides and sets all the outputs to zeros. And since we've got the clear pins on all of our other registers hooked up to a master reset button, I'll just hook this up in the same way. So when we push that master reset button, it clears the flags register too. And last but not least, I'll add some labels. This is our new flags register. And of course, we can label the bits here as our carry flag and 0 flag. So let's test it out. I'll hook up power, and we'll set up that same scenario that we looked at before we built the flags register, so we can test out the flags register and also just see how things might work differently with it. So just like before, I'll put in this program to load a 254 into the A register, and then do an add, which results in a carry. Okay, so again, just like before, we're imagining we're running a program, and we've got a value of 254 now in the A register when we come across these commands here. So this add followed by a jump carry. So we'll just step through step by step. So the first 2 steps of the add fetch the add instruction. And now we can see we've got the 0010, which is the opcode for add, and 1111, which is 15. So we've got the add 15 there. So the next micro instruction in our add instruction is instruction register out, memory address register in. So we're going to move this 15 from the instruction register to the memory address register. There it is. And that lets us get at the value of address 15 in memory. And so then the next micro instruction, RAM out B in, takes that value from memory, which is a 3 in this case, and puts it in the B register. So now that we've done that, again, you can see we've got 254 plus 3 equals 1, and the carry bit is set. So this is just like what we saw before. And like before, the next instruction is a jump if carry. So that means that we'll want to actually do the jump. So let's look at this last micro instruction of the add instruction. So this micro instruction takes the result of the addition and puts it in the A register. So it takes this 1, puts it in the A register. But this time on this step, we also want to take the results of the status bits, in this case the carry bit, which is set, and the 0 bit, which is not set, and put those into the flags register. So along with the sum out and the A in control bits, we also want to set the flags in signal here. So let's do that. So we'll set that. It's active low, so I'm setting it low. And then now I'll pulse the clock once more to execute the sum out, A in, flags in control bits. And okay, now we've got that. So we've got the answer, which was 1 in the A register. And now we've got the carry bit in the flags register, even though now the carry bit down here isn't set anymore. And so now that we've executed this last step of the add, we can disable the flags register again, and it'll hold on to these values. So if we continued running this hypothetical program, we'd have the information we need to know what to do with this jump carry instruction sitting right here in the flags register. Now you may have noticed that it now becomes important to control when we update the flags register. And for this to work, I had to be careful to just enable the flags register to update on this specific micro instruction here. Now, for that to be automatic, what we'll need to do is add this enable signal that I'm just sort of manually controlling now to our control word down here that controls all of our other control signals. Now, conveniently, since we're using 2 EPROMs for a microcode, we can have up to 16 bits in our control word, and I'm only currently using 15 of them. So that leaves us with a bit available here that we can use to control when the flags register updates. So I'll connect that bit over to the control word and add a 16th LED so we can see what this last control bit is doing, just like the rest of them. Now I know a few people suggested using this unused bit to reset the microinstruction counter at the end of shorter instructions, which I think is a great optimization, but I didn't do that because I was planning to use it for this. And I'll also add a current limiting resistor to ground here, since otherwise the output of the EPROM will drive too much current through the LED. And then I'll update the label for this new signal as FI for flags register in. So there we go. And now all of these bits in the control word are active high signals. So to keep things consistent, since the data enable line over on the 74LS173 is active low, I want this flags in signal here to go through an inverter before hooking it up to the control signal on the register itself. Fortunately, there's a spare inverter on this 74LS04 chip right here. So the control signal can go into the inverter. So here we've got the control signal now going into the inverter. And then coming out of the inverter, we'll have an active low signal, which we can run up to the data enable pin on our flags register. And I'll just tidy some of this up. And there we go. And so now our microcode here will be able to control exactly when we load new data into the flags register. So of course, we'll need to update the microcode and reprogram these microcode EPROMs for that. But we're going to need to make some other changes to the microcode too. We'll need to come up with the microcode for our new conditional jump instructions. So to think about how that'll work, let's look at how the jump instruction works. The execution of every instruction is defined by microcode, which is stored in these EPROMs here. And the EPROMs are basically just a big lookup table. We've got 4 bits from the instruction register, which are these 4 bits here, going into 4 address lines of the EPROMs. And then we've got 3 bits from the step, which are these 3 bits here, and they're going into 3 more address lines of the EPROMs. And then based on whatever the instruction and step bits are, then the EPROMs are going to output a particular control word, which you can see over here. So let's say there's a jump 0 instruction sitting in memory. So first it gets loaded into the instruction register. And that's because the step counter right now starts out at 0. And the EPROMs are programmed that for any possible instruction, if the step is at 0, then output this control word. And this control word says counter out memory address register in. So you can see that here, counter out memory address register in, and that's because we're on step 0. So the contents of the program counter get put into the memory address register when the clock ticks. So now we're at step 1, and these LEDs are turned around backwards. This is really step 1. And for an input of step 1 with anything in the instruction register, so step 1, anything in the instruction register, the EPROMs are going to output this control word here, and that's what we see down here. And this says RAM out, instruction register in, and counter enable, which increments the program counter. So with the next clock tick, the contents of RAM gets moved into the instruction register, and we move on to step 2. So at step 2 now, we've got 0110 in the top half of the instruction register, and 010 is our step. And so anytime that we've got 0110 as our instruction and 010 as our step, like we do, then the microcode EPROMs are going to output this control word here. And this control word says take the bottom half of the instruction register and put that into the program counter. In other words, the next instruction executed will be at address 0 here, because that's what's in the bottom half of the instruction register. So if we execute that, you can see this 0 goes into the program counter. Now that's an unconditional jump. It's always going to jump no matter what's going on with the flags register over here. But how can we build a conditional jump? Right now, the control word is the result of a lookup table, that depends on the instruction that we're executing and what step of that instruction we're on. But since it's the control word here that controls whether the program counter is being updated or not, we need this control word to also depend not only on just the instruction in the step, but also on the condition, whether a particular flag is set in the flags register. So what we need to do is change the way that our microcode works. So instead of being a lookup table like it is now, that takes a 4-bit instruction and a 3-bit step and outputs a control word, we need it to be a lookup table that takes a 4-bit instruction, a 3-bit step, and the 2-bit flag register and outputs a control word. Luckily, the EPROMs we're using have 11 address lines, and we're only using 8 of them. We've got 4 for the instruction here, we've got 3 for the step, and then this 8th one, we're just tying low on this one and high on this one, so we could program both EPROMs the same. But we've got 3 more address lines that we're not using at all, 8, 9, and 10 here, and they're just tied low. So instead, we could hook up address 8 and 9 to the carry flag and the 0 flag from our flags register. And that way, the behavior of an instruction could be different depending on whether one of the flags is set. In most cases, it'll be the same, so we'll just have to program the same thing regardless of what the flags are set to. But for our new conditional jump instructions, we'll be able to do something different. So for jump carry, when the carry flag is set, we can have it actually change the program counter, but for jump carry when the carry flag is not set, we can have it do nothing. So let's hook that up. Address 8 and 9 are these 2 pins here and these 2 pins here, and they're currently tied to ground, so I'll remove that to start with. Next, I'll tie address 8 on the left EPROM to address 8 on the right, and address 9 on the left to address 9 on the right, since we want to consider the flags register the same for both halves of the control word. And then let's hook the carry flag over here around to address 8 of the EPROMs. And same thing with the 0 flag. I'll hook that up to address 9 of the EPROMs. All right, so now we've got the flags register hooked up as another input to our control word lookup table. So now our control word is going to depend on the instruction we're on, what step of that instruction we're on, and what the flags register might happen to be. Now, if we hook this up, as long as the flags register is 0, then everything's going to work out just like it did before. And actually, since none of our instructions are setting this flags in bit yet, because we haven't reprogrammed our microcode at all, the flags will actually always be 0. So right now, the computer actually works exactly like it did at the beginning of the video. Except, of course, we've added a bunch of hardware that makes it possible now to create new instructions that will let us do conditional jumps. So now we've got all the hardware in place, we just have to update our microcode. And so in the next video, I'll actually go ahead and reprogram the microcode EPROMs to make use of the flags register and create those new instructions that'll let us do conditional jumps. And I'll also write and test some programs that make use of those conditional jumps. But one last thing that'll leave you to sort of ponder, I've noticed that a really common feature of any complex system is the presence of feedback loops. Whether it's a biological process, economies, or the climate, any truly complex system always seems to involve feedback loops. And so I find it kind of interesting that the hardware that we build in this video essentially creates a feedback loop. We've got these flags here, which are now an input to this function that determines the control word, which in turn affects how the flags get updated. And so there's kind of a bit of a feedback loop going on here. And I don't know, I just think that's interesting that we set out to make this thing Turing complete, which is fundamentally a dramatic increase in the complexity of what it can do. And it turns out that in order to do that, it looks like we ended up adding a feedback loop. So I'm not really sure what to make of that, but I thought it was kind of interesting just to notice. So anyway, in the next video, we'll go ahead and reprogram the EPROMs to handle this new flags register and add our conditional jump instructions and actually demonstrate the new powers of our computer. And with that next video, I expect I'll be pretty close to done with what I planned for this computer project. But I'd love to hear your thoughts on future projects or other videos that you'd like to see me do. There's a link in the video description to a Reddit thread where you can make video suggestions. Obviously no promises, but I'd love to hear what you all are interested in seeing.